As the final speaker, it's my duty to thank the organizers, none of whom happen to be in the room right now. So if they do show up, we'll thank them later. We'll start slowly. We want to construct an R matrix, and we saw in Eva's talk what an R matrix was. Let me just recall this. I'll start with a single vector space. The same construction will work over some collection over, and the vector space will be over a single field. And I'll have an operator that will depend on some spectral parameter u, some formal parameter. And it's an R matrix if it satisfies the Yang-Baxter equation. That is, I can take a tensor product of three copies of this vector space. I can act in all pairs of two factors in a certain order. Or I can reverse the order of these operations. So this is just what Eva called Rmatrix 3. Okay, and I'll want to also impose the condition just that these operators are normalized so that at infinity they evaluate to 1. Okay, now that Travis is back, as the final speaker, we can thank Travis, Peng, and David Gwynn, and Olivier and Absentia for organizing a phenomenal and very stimulating conference. As well as the staff here at CERN for keeping us well fed, comfortably lodged, videotaped. So back to R matrices. So I can view this R matrix as some rational valued function in the spectral parameter, or sometimes if I set the parentheses ui to be some kind of evaluation representation, I can think of it as taking values in some parameter ui, and it can view the R matrix as some operator. Like so. So we'll toggle between these two interpretations. And so the nice thing about having an R matrix is you immediately deduce lots of integrable structure. So once you have an R matrix, there's this quantum inverse scattering method of Faddeev, Reshetigin, and Takhtajan that produces a whole package. So for example, it produces the action of some Hopf algebra, which I'll call Y, on these vector spaces and tensor products thereof. Moreover, so this y, so maybe the generators arise as matrix elements of RU. I can read off also commutative subalgebras. So we get what are called Baxter subalgebras in Y. And these arise if I have some endomorphism in my vector space that commutes with the R matrix, then taking matrix elements of this phi produces commutative subalgebras. Okay. So for example, if my fields are the field of rational functions in two variables, and my vector space is C2, one example is the familiar R matrix associated to the XXX spin chain. I can write like so. Where the identity just fixes this tensor product and this permutation swaps it. And the resulting Y I get is what's called the Yangian of GL2. So this is some Hopf algebra deformation of the universal enveloping algebra of loops in GL2, and this is some familiar thing. Okay. And so what I want to talk about today is a certain way to obtain solutions to this Yang-Baxter equation using geometry. So I'm going to give some background on the general context into which the results I'll present fit. And so that's quite a long story, but I'll present a very condensed version of work of Maulik and Okounkov constructing R matrices in the cohomology, acting in the cohomology of Nakajima varieties. Yeah.
Sorry, in that example, can you get the Kantian center by just identifying some and well, that as a Baxter subalgebra?
Yes.
And what would the phi would be?
What would the
phi would be? The phi would be
phi in this case? Okay, I can tell you geometrically. So if you think of this as cohomology of some Grassmannian, what it would be is multiplication by Chern classes of the tautological bundle over this Grassmannian. There should be some answer algebraically, but I don't know it off the top of my head.
Baxter subalgebra would be central in this case, or just commutative?
Baxter subalgebra would be just commutative. Yeah, not necessarily. Yeah. Yeah. Sorry?
Isn't it going to be the H's in the Yangian?
Is who going to be the H's in the Yangian?
The Baxter subalgebra.
No. So yeah, Maulik and Okounkov construct R matrices acting in cohomology of Nakajima varieties. This is, I guess if you were to come here in a few months, you could get a book on this half price in the auditorium. But for now, we'll settle for a basic case. What's the vector space V going to be? It's going to be torus equivariant cohomology of.
So it's appearing in asterisk in a few months. That's what you said.
It's appearing in asterisk at some point.
Okay.
Yeah. So on a cosmic scale, a few months, but I don't know. So we have some torus that scales the plane. This acts on the Hilbert scheme, and we get torus equivariant cohomology of the Hilbert scheme. And I want to combine all the Hilbert schemes for various numbers of points together to produce an infinite dimensional vector space V. And this will be some algebra over the field K, which will be the fraction field of torus equivariant cohomology of a point. Okay, and not only can I realize V geometrically, but I can realize its tensor products geometrically. So I consider Instanton moduli space. So this is the moduli space of rank R, torsion-free sheaves on P2 with a framing along line infinity with second Chern class n. And so if this seems esoteric, it's just this quiver variety. And I can set MR just to be, as we did for the Hilbert scheme, to be the direct sum over all n of MRN. So in particular, M1 is just Hilb of C2. And the tensor product of these modules is isomorphic to the equivariant cohomology of this large moduli space. And here, this C star R contributes the equivariant variables. So these spectral parameters are realized as equivariant variables here, and this is the torus that acts on the framing. So in particular, it's trivial for the Hilbert scheme, but you can still keep this parameter around. Okay. And so Maulik and Okounkov produce an R matrix acting in this tensor product of V with itself. And I'm not going to review the whole construction here, but I'll kind of say some words. So there's two constructions. The second I'll say much more about. The first I won't say as much about. It uses stable envelopes. So these are the same as the stable classes that appeared in Eva's talk. And let me kind of say the salient properties that one deduces from these stable envelopes. So one, the Yang-Baxter equation comes almost for free once you study some basic properties of these stable envelopes. So defining stable envelopes and checking these properties takes some work, But once you do that, the Yang-Baxter comes for free. And then second is that vacuum matrix elements of Ru are given by multiplication by Turing classes of tautological bundles. This is classical multiplication. So let me say more precisely what I mean by 2. So stable envelopes give me some condition as to how this R matrix should act on components of a fixed locus with respect to this framing torus. And once I unravel that definition, I see that if I take the vacuum element to be just a generator of the Hilbert 0 of C2, that is of a point, and I compute this matrix element, this is supposed to be equal to a ratio of Euler classes of these tautological bundles twisted by some characters of this torus. And so if I expand this in 1 over u, well, I can write this as a product over I, where these xi are Chern roots, of my tautological bundle. And if I expand this in 1 over u, I can read off symmetric polynomials in these Chern roots that give me classical multiplication by this bundle. So for example, I get 1 plus h bar n of u, where this h bar is the weight of the symplectic form on C2. That is this T1T plus T2 that showed up in this R matrix earlier as well. And I can continue. I get and then finally this Turing class shows up, and so on. And so the more I expand in U, the higher and higher order Turing classes I get of these bundles. So once we have this R matrix, what do we get? Well, running this quantum inverse scattering method that I talked about in the beginning, we get some Yangian acting on the cohomology of these instanton moduli spaces. And that cohomology, that Hopf algebra has a lot of names. One of them is the Yangian of GL1 hat. And so Schiffmann and so this Yangian shows up in all sorts of other guises and constructions. For example, Schiffmann and Virasoro showed that the Yangian constructed in this way is isomorphic to the cohomological Hall algebra constructed by Schiffmann and Virasoro. It's also the same as what's called the affine Yangian of GL1 defined by Fagan and Symplectic. And so this algebra appears in a lot of places.
Can you remind me just briefly about Virasoro? The coha is for what? What sort of Hall algebra of what kind of gadgets?
Cohomological,
It's like something to do with curves or?
yeah, so it's a Hall algebra of an elliptic curve.
Right, and the one that
And-
is the case of projective algebra.
And so I should mention that if the quiver you start with is finite type, you can run the same procedure and you recover the Yangian action found by Varaniello. And then one also has Baxter subalgebras. So if I let, say, phi sub q be the operator that acts on v, by scaling the cohomology of the Hilbert scheme of endpoints by some element q to the n, and it's very easy to check that the resulting tensor product of this operator with itself commutes with the Rmatrix. And it's a theorem of Maulik and Okounkov that the resulting family of commutative subalgebras coincide with the operators of quantum multiplication. By Chern classes of the tautological bundle. And so this quantum cohomology ring showed up in Katerina's talk. It's some deformation of the usual cohomology ring whose structure constants are given by equivariant Gromov-Witten invariance. Maybe if I'm going to be precise, I want to put a 1 here. Okay. And so here's the kind of question I'd like to answer is what parts of this story can be extended beyond the setting of Nakajima varieties or more generally beyond the setting of conical symplectic resolutions. So let me just today concentrate on Hilbert schemes. So what parts can be generalized to Hilbert?
Okay, can you just clarify the last theorem? So you're saying some algebras are given, so quantum multiplication, how I do I interpret these two sides? Quantum multiplication?
So here I can specialize kind of q to some complex number. And if I fix a q, then I get some operator that generates a commutative subalgebra. And as I vary q, that corresponds to the family of subalgebras over here.
Can we be confused? What is the relation with the phi q that you defined just before? These two operators, phi q and multiplication by c1 is different, or it's a little bit confused?
Yeah, no, but Eric is right that somehow this Q is not the same as this Q.
That's my question.
Yeah, it's not. Maybe I should say Z here or something like this. Yeah.
Are they related?
So certainly at 0 they're related. So somehow I'm supposed to recover, if I set 0 here, I recover classical multiplication. And if I set to 0 here, I also recover classical multiplication. But as you vary, I don't know off the top of my head. Sorry. Yeah.
The formal neighborhood, you probably have the formula in the formal neighborhood of 0. One as double 0, but maybe it doesn't make sense outside the.
Possibly, yeah. I mean, yeah, like certainly this is defined everywhere and this has poles somewhere, so yeah. Okay. So yeah, what parts can be generalized to Hilbert? So one motivation for asking this question is to better understand the quantum cohomology ring of the Hilbert scheme of points on a K3 surface. So in general, there's some kind of expected relations between quantum cohomology of the Hilbert scheme of points on a surface and Donaldson-Thomas theory of threefolds fibered in these surfaces over curves. And when your surface is symplectic, there's this kind of correspondence is supposed to be as nice as possible. But one can't just use the Maulik and Okounkov kind of package here because there's no torus action on a K3 surface. So one needs some way to get around this. So the whole package can't reproduce the whole package. And so I'm thinking about what parts can be. And so here's some kind of start of results in this direction.
That's quantum multiplication by C1 of what?
Of the tautological bundle.
This one element.
Yeah, so this generates the quantum multiplication ring of Instanton
The whole
matrices.
algebra can be given by
The whole Baxter subalgebra, or the whole quantum cohomology ring. Mm-hmm. And yeah, in general, if I have any Nakajima variety, its quantum cohomology is generated by Chern classes of the tautological bundles. Okay, but so what can we do is one, we can still construct an R matrix for general S. And two, we can modify this construction to obtain classical multiplication by Chern classes of tautological bundles associated to other line bundles over the surface. So I mentioned, here when z equals 0 and q equal when z equals 0 over here, you recover classical multiplication by these divisors, and you can do the same on this side. In general, you can't expect to upgrade this to an arbitrary surface, but at this z equals 0 case, you still can match. So let me explain how to do this. Okay. So what's the setup? When I say general S, there's some kind of mild assumption we have to put. S either has to be proper, or I guess the proper is a subcase of what I'm about to say, but I have some torus that acts on S such that the fixed locus is proper. Right, and the reason I want to do this is because I want to have some notion of integration over the surface. So then I can integrate over the surface. And moreover, I can have some pairing of two classes on the surface given by minus the integral of their product. Okay, and then the equivariant cohomology ring has the structure of Frobenius algebra. Over equivariant cohomology of a point. So I'll drop all equivariants now and to just kind of assume everything's equivariant. And so in particular, if the torus acts on the surface with proper fixed locus, then the same is true for the Hilbert scheme. And so if I, as I did before, group all the cohomology of Hilbert schemes, what I get is a Fock space for a Heisenberg algebra whose generators are labeled by elements of the cohomology of my surface. Okay. So let me just fix the notation. For some positive n and for some cohomology class of my surface, I'll let alpha minus n be an operator going from the cohomology of the Hilbert scheme of m points to the cohomology of the Hilbert scheme of m plus n points. And it will be given so essentially what I want to do is add a fat point of length n along the cohomology class that's along the homology class that's Poincare dual to gamma. In other words, I have some cycle in this triple product, and this consists of triples whose support only differs by a single point P with multiplicity n. And this comes with 3 projection maps onto each of its factors. And if I apply this operator to some cohomology class X of the Hilbert scheme, what I do is I pull back my cohomology class, I pull back the cohomology class sitting on the surface, and I intersect with the fundamental class of this cycle. And finally, I push forward along my third projection map. And so maybe I need to localize some of these cohomology groups for everything to be well defined, but that's okay. And for positive n, I can define using an essentially similar construction, or by taking the adjoint operators to these. And it's a theorem of Nakajima and Granovsky that these operators form a Heisenberg algebra. In other words, if I try to commute two of them past each other, if I plus j is not 0, then I get nothing. And otherwise, I get a Heisenberg algebra incorporating the pairing on this surface. Okay. But before, we weren't just looking at VS, we were looking at these evaluation representations with some spectral parameter. And so fortunately, we have one degree of freedom to kind of tell us how the spectral parameter should be incorporated, and that will come in by the 0 modes. So I've told you what, I said that n was a natural number here. When n is 0, these 0 modes will act by a scalar that's some function in U. Okay. All right, and so now I want to upgrade this construction to an R matrix. Okay, or instead I'll phrase it in this form where I'm acting on the tensor product of two evaluation representations. And the first thing to do will be to break up this tensor product in a different way. So I want to let Vs with either a plus or minus as a superscript be the algebra, maybe be the subspace generated by either alpha n tensor 1 plus 1 tensor alpha n, or minus, depending upon if I have a plus or minus here. And I want to take this and act on the vacuum vector in the tensor product. And so then I can rewrite this tensor product as a tensor product of this positive part, where now the 0 modes act by U1 plus U2, and on the other factor, they act by U1 minus U2. And so to give this R matrix, the idea is to extend a second construction of the R matrix from Maulik and Okounkov that's not, I think, as well known, but will work for a general surface. And so how does this construction arise? Well, when S is equal to C2, what can one say?
On the right hand, VS plus plus VS.
Is it a plus or a tensor?
It's a plus on the right hand.
Here?
Yeah.
That's a tensor.
That's a tensor?
That's a tensor.
So that's just a tensor as a vector.
Tensors vector spaces over, this large, over, frac of ht of a point.
Maybe the question
So
is
you
what
use the
kind of
algebra
structure?
structure. You use the algebra structure somewhere.
This is an isomorphism of vector spaces. And then, yeah, isomorphism of vector spaces.
Okay, to define it, you need to.
Yeah. So, somehow I have an algebra that acts here and a separate one that acts here as well. but it kind of mixes. Okay, so the first thing so using kind of some general properties of R matrices, one can show that RU commutes with half of these operators, that is those with a plus. So that tells us that R has to act only in this second factor. Okay, then the second is that any operator satisfying 1, that is one that can only acts in here, that is that can only be written in terms of these alpha minus, is determined uniquely by its vacuum matrix element.
You mean satisfying one and Yang-Baxter, or just any operator satisfying?
Any operator that commutes with these kind of Steinberg type correspondences, these alpha n plus. Yeah. Okay, and then finally one can pin down the exact form of RU by computing how the stable envelopes intertwine classical multiplication with a tautological bundle on the moduli space of rank 2 sheaves. And what one sees in this case is that the R matrix can be expressed as a certain reflection operator. And so one place to read about this construction is in Maulik and Okunkov's work. This construction was also used in work of Braverman, Finkelberg, and Nakajima. Studying the cohomology of Instanton moduli spaces. So there's lots of papers with these three authors. This one is called Instanton moduli spaces in W algebras. And so far, these are the only two places where I've seen this construction used. And so the nice thing about this construction is it can kind of be adapted nicely to a general surface. And if you are careful about how you modify this construction, you can actually get a little more out of it. So let me tell you what this construction is. So a reflection operator will be a certain intertwiner of highest weight Virasoro modules. So anytime you have a Heisenberg algebra, you can use the Fagan-Fuchs construction to produce a Virasoro algebra action. And how do I do that? Well, in this particular case, I'm going to write the generators, I'm going to write the expression in terms of these minus generators here. So maybe I'll set alpha n minus gamma. To be the Heisenberg generators generating this minus part. And it's some quadratic expression in these Heisenberg generators. So here, gamma I and gamma I prime are the Coonth components of the coproduct of gamma under the coproduct. So I have some kind of quadratic word, and then I can introduce a formal parameter kappa that we can think of as the weight of the cotangent bundle of our space. And so this kappa here will just be a formal parameter for now. In Maulik and Okounkov, it's specialized to be the weight of the symplectic form, but you don't actually need to do this for this construction to work, and it's important not to if you want a meaningful answer for K3 surfaces, for example. And then finally, there's some kind of correction we'd like to the zero mode. That's not particularly important. So it just looks like the usual way to pass from Heisenberg to Virasoro with some kind of decorations coming from cohomology of the surface. Okay. And these Virasoro algebras also show up geometrically when you compute the commutators of this Heisenberg algebra with the first Chern class of this tautological bundle, or equivalently intersection with the boundary. So these have some kind of geometric meaning as well. So here's a proposition that in this level of generality is essentially due to Maulik and Okounkov, but generalizes, it's a pretty easy generalization from the argument for usual Virasoro, and that's that these operators I've written down do indeed satisfy a Virasoro type relation. So if I commute two of these past each other, I get this usual first Virasoro term, only I need to multiply the cohomology labels. And then if m plus n is not 0, then I'm done. But otherwise, I need to multiply by this usual factor, and then there's some expression coming from cohomology of the surface. And so it's this expression here that should be thought of as the central charge. For now, it's just some formal parameter. In Maulik and Okounkov, it's specialized to be the weight of the symplectic form.
What is the integral of
Treat it, maybe think of this as the formal parameter times the identity. So it just comes out of the integral. So equivalently, I could have, so for example, in C2, this is just some equivariant parameter, so it comes out of the integral for free. So you could also think of, this is 6 kappa squared times the integral. Okay. And so we have the central charge. If we want to classify Virasoro modules, we also need the conformal dimension, right? So this second factor, generated by these minus Heisenbergs, is a lowest weight module for this Virasoro algebra. generated by these ln gamma. And to compute the conformal dimension, we need to compute how these zero modes act. And so directly reading from that formula, one gets the following. Then there's some factor corresponding to the integral times my vacuum. And so this expression here is the conformal dimension. And so once you have the central charge and conformal dimension, you know these completely classify lowest weight modules. And in particular, we see that kappa only enters quadratically. And so in particular, if I were to define a new operator, say ln hat of gamma, ln bar of gamma, that was the same as ln gamma, only I flip the sign of kappa. So in this linear term, I just flip the sign. Then the resulting module should be isomorphic. That is, we have an isomorphism that I'll call R minus S from this second factor to itself that's given by taking a word in these Virasoro generators applied to the vacuum to the same word in these kind of right-moving generators. That is where I flip the sign of kappa. And so I've said how this R, so this is how R is going to act on the second factor. And on the first factor, I just want to mimic what happens in the C2 case. It acts trivially. So that is to say, I want to set this RS to be the identity on this first factor, and will act by this reflection operator. So sorry, that's plus here. Okay. And so this is related to the reflection operator from conformal field theory. Same kind of expression shows up. Okay, so I have some R matrix, and you can guess what the theorem should be. The theorem is that this R matrix satisfies the Yang-Baxter equation for any S. Mine.
You usually put an A next to it.
Okay. Thanks, Dave. And so I also made a point to talk about before how if you look at the vacuum matrix elements, you can read off expansions of the multiplication of Chern class and tautological bundles, and the same is true here. So the vacuum matrix element of this RS encodes multiplication by Chern classes of tautological bundles. This is a consequence of Lens results.
It's not independent.
Of Lens formula for, in some ways it is, right? So Smirnov has this computation of the Instanton Rmatrix that just passes through stable basis and rederives Lens result. And once you have that, then you can do the same thing here. So somehow this is completely independent of Lens result. The argument is kind of both of these formulas are sufficiently universal that if you use Ellingsford-Gertscher-Len, they're going to be equal. Yeah. And even if you want an exact formula, you also don't need to use Len. You can use Smirnov. Yeah. And then finally, so here we have multiplication by a single tautological bundle. But over Hilbert's given points in an arbitrary surface, there's other tautological bundles I can pick if I have bundles on my surface. And I can modify this construction. And all I need to do is modify how the zero modes act. So before, I had these zero modes act by minus u times this integral. And if instead I replace this by the same expression, only I shift by the Chern class of my line bundle, I repeat the same construction to get a new operator that maybe I'll label with the line bundle. And the result doesn't satisfy Yang-Baxter anymore. But the vacuum matrix elements still will encode this classical multiplication. Some kind of shifted. So you just have to shift the spectral parameter by this cohomology class, and you'll recover. So it's not so far from Yang-Baxter, but so if I look at the vacuum matrix elements, then again I get this similar kind of formula I wrote earlier. But this h bar gets replaced by kappa, and so on. So we get the same expansion just with h bar replaced by kappa, which is important if you're working over a K3 surface. You don't want all these terms to vanish. And I have my trivial bundle replaced by L. And so maybe I should say the matrix element here of this restriction. So the proof that this satisfies Yang-Baxter eventually, the kind of strategy starts with a surface and reduces it to C2, at which point you have to match up with the stable envelope construction. So one kind of open, kind of interesting question to me is there a proof that this construction, even for C2, that doesn't use stable basis? So here there's some kind of relation between Virasoro and Yang-Baxter, and it's kind of mysterious, and I'd like to understand it better. Also, if you were paying careful attention, this construction, all it really used was the Frobenius algebra data of cohomology of the surface. And so the fact that we had a surface wasn't important until I run this proof. And so the construction can be reproduced if I replace cohomology of a surface, I can instead look at cohomology of some higher dimensional variety X, or I can even look at some general skew symmetric graded Frobenius algebra A that doesn't come from geometry at all. And you can run the same construction, and you can ask whether these R matrices still satisfy Yang-Baxter. So I tried it for like some projective spaces, and it still does, but then I realized that those Frobenius algebras can just be written in terms of Frobenius algebras of a surface, so that's not so interesting. So yeah, I don't even know of an example of a skew symmetric graded Frobenius algebra that doesn't come from cohomology of a variety or specialization of equivariant cohomology of some variety. So any kind of thoughts on this would be interesting. So the question here is, does R U still satisfy Yang-Baxter? And an answer either way would be interesting. If somehow this construction used something special about the cohomology of surfaces, that would be cool. And if it holds in general, that's also interesting to me. And then finally, does this constrain quantum cohomology of Hilbert K3 in any meaningful way? So Oberdijk and Oberdijk and Pixton have some conjectures, and some of these conjectures are given by some matchings which are vaguely reminiscent of what's going on here for Virasoro. So it's possible that the resulting Yang you get from this construction can help you understand better some quantum multiplication operators in this Hilbert scheme. But I'll stop there. Thanks for your attention.